Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. It's my pleasure to introduce Olga Brookman. She did PhD at Ben Gurion, where I used to teach. And she wrote to me that she will be in Seattle. And she has such and such talk to give. I thought, very interesting. I don't know anything about this, but I'm happy to learn. And it seemed to me sufficiently relevant to Microsoft. Actually expected bigger audience, but maybe many people will be watching this on later on, and maybe will come. In any case, welcome, and looking forward to your talk.
Okay, so I'll be presenting basically the work I did during my PhD. The topic is self-stabilizing autonomic recovery. It's a bit vague, so I hope that I will clarify what I'm talking about. So the problem, the general problem my work tried to address is lack of ideal software. Ideally, a system should anticipate every possible scenario and work always. In reality, engineers fail to create such system despite their effort. Having bugs, scrap state, leak resources are quite common in software. Especially it's common and very, very difficult to find, very difficult to debug and fix in long-lived running programs such as operating systems, plane flight control systems, cars, because the full verification of such systems is impossible due to huge state space of the environment. The problem with bugs is not that they are annoying. The problem is that they actually cost quite a lot of money. In 2002 study by USA National Institute of Standards and Technology showed that software bugs cost US economy only $60 billion annually. In real life, we actually rely on accumulated knowledge of human operators to overcome faults. So several examples of what faulty software can cause. In 1996, the European Ariane 5 rocket exploded 40 seconds into its maiden flight due to software bug. Several Mars rovers, robots that were sent to Mars, actually lost contact, were lost, freezed, all due to some kind of software problems. In 2003, there was a blackout due to programming error programming error has been identified as the cause of northeast power blackout. The failure occurred when multiple computer systems trying to access the same information at once got the equivalent of busy signal. In 2005, a plane suddenly took a mind of its own and zoomed 3,000 feet upward. Even when pilot disconnected autopilot, it moved controls to lower the plane. The plane still didn't go as expected. It turned out that a defective software program has provided incorrect data about the aircraft speed and acceleration, confusing flight computers. And there was also another case of Daimler Chrysler had to recall 128,000 sports utility vehicles because of a problem with the software governing the fuel pump and powertrain control. The defect could cause the engine to stall unexpectedly. So basically, there is quite a lot of research in systems that aim to solve those problems. Automatic recovery, self-managing systems, self-healing systems, evolving systems, dependable systems. But basically, there is a direction that implies need for robust and stable software and not only performance-optimized software. So in our work, we've provided a theoretical approach based on classic fault tolerance theory. We made problem formalization, and we presented several generic architectures to address this problem, and we also provided correctness proof guidelines. We treated basically our work can be divided into two main sections. One is to ensure correctness of existing software packages, where a package can be either black box or transparent box. And the other part is to find control program dynamically upon the change in the environment. The work we did was basically theoretical. We did some proof and concept prototypes, but we didn't have resources and ability to do full-scale system research. But we still think that the ideas can be implemented can be used in long-running continuously executing systems that should stay up and running while absorbing unexpected faults. And it could be cloud computing, control systems, storage systems, grid systems, and so on. So going into details into specific works that I did during my PhD. The first one is self-stabilizing autonomic recovery for eventual Byzantine software, the case of black box. So what is correct software? Basically, a software should respect its specifications. The specifications can be divided into classes: safety specifications and liveness specifications. Simple example of safety specification for atomic power station is that the atomic station should never explode. And the liveness, the atomic station should produce some electricity over time. If we formalize fault model that reflects reality, we would say that software packages can be trusted to work as required after restart, meaning that they are eventually Byzantine, but they are not immediately Byzantine. Non-Byzantine execution should be long enough. What do you mean by Byzantine? Faulty. Okay. Non-Byzantine execution should be long enough to produce sufficient work. The non-Byzantine section of execution can be attributed to testing done by the manufacturer. System administrators and users use reboot or some other kind of a non-intrusive recovery action to deal with faults in such systems. What we suggest basically is to provide automatic monitoring and recovery layer that is completely correct, and that ensures that the underlying monitor system is in a legal state, and if it's not, it will recover it. So what we suggest is self-stabilizing autonomic recovery for black box software. Package is monitored basically by recording its I/O system calls. It can be done either using strace calls in Linux, or if software package implementation tool is known, then runtime reflection tools can be used. So the basic idea is that we have self-stabilizing processor and operating system. I will explain later why is that important. And that we have OS resident monitor restarter that is an integral part of kernel. The OS resident monitor restarter receives as an input list of predicates and recovery actions for critical processes, predicates that state safety and liveness properties of the critical processes. Then it starts monitors for all critical processes that check continuously the predicates that are relevant for a certain process. The thing is, this monitor recovery layer is generic and completely independent of specific system implementations. All you have to do to customize it for a certain system is provide a list of predicates and recovery actions. Okay, the important thing that we came up the idea which we feel strongly about is that in most works in this area, they say, okay, we have a monitoring system, the monitoring layer. The thing is, the monitoring layer itself is a program basically, and can contain faults. contain faults. So the idea is to make this monitoring recovery layer self-stabilizing. So the thing is, if self-stabilization is basically an area in fault tolerance, is an area in fault tolerance that says that a program can execute, the program has to execute continuously. It may become faulty, but eventually it will converge to a legal state. So the thing, what we want to do is that the recovery layer, monitoring recovery layer, may become faulty, but will always converge to a correct state, meaning that which implies that the monitoring system will converge to a legal state as well. So if some process fails, the monitor will recognize that, do some kind of will execute the recovery action, hopefully restoring the system to the legal state. So, as I mentioned, every critical process has to have a monitor, checking its predicates and invoking recovery actions if needed, but it's not enough. We must have monitors for subsystems as well. Each one of the processes can be in a consistent state, but the combined state may be faulty. Thus, you have to have a monitor recover for subsystems and subsystems of subsystems. Okay, the dependency graph of processes and subsystems must be directly the cyclic graph to imply a deterministic recovery path. So monitoring of safety properties is quite obvious. Can be achieved by simply adding monitoring layer that checks predicates and invokes recovery actions. Monitoring and detecting lack of liveness is much more complicated, because the liveness basically comes in a sort of form. Eventually, something happens, or so and so until other event happens. So what we have to do is to look at the state of a process or subsystem over time and record its state and see if liveness events. Okay, so what is live lock? It's when we see this, that the process or subsystem enters the same state twice without having liveness event in between. Because if the system is deterministic, that means it will have the same execution again and again and again without having liveness event in the middle. So in order to monitor liveness and detect live locks, a monitor should accumulate history log, where each entry is a snapshot of subsystem variables, subsystem state. One can record the whole state or important sections of state. When liveness event occurs, history log is streamed. Basically, we don't have to maintain history of execution that is alive, that is progressing. But when live lock identified by seeing identical entries in history log, and then process or subsystem, by identifying identical entries in history log, and the process or subsystem executed at that section of time, should have executed at the same section of time. Because if it simply, it is in the same state, but it hasn't executed, so the process just didn't get enough CPU time or resources or something. Okay, so as I mentioned before, the subsystem hierarchy dependency graph should be directed at the cyclic graph. Recovery actions. First of all, what is appropriate recovery actions in such framework? First of all, subsystem should wait for completion of restarts of its components. Otherwise, that will trigger a restart of the whole system every time. Recovery actions should be non-intrusive, meaning that they should not alternate system original control flow design. Because if they do, they basically change the system, and there are no guarantees on system execution after that. and also it simply can introduce new bugs into the system. Recovery actions may vary depending on component internal state. It can be rescheduling, rolling back, killing process or subsystem and restarting it. Few restart attempts with more drastic recovery actions can be made. This framework can be applied for distributed systems. So each one of the machines will have its own OS resident monitor restarter and list of predicates and recovery actions for its processes and subsystems. But in case we want to have it for distributed case, we will have to have a monitor recovery for the whole system. Basically, we have to have some central node that monitors the health of a distributed system with list of global predicates. So, as I mentioned before, the monitor recovery layer should be self-stabilizing, meaning because we need to have this layer always up and running and eventually executing legally. So why is it self-stabilizing? We assume that OS resident monitor recovery is we show that OS resident monitor recovery is we assume that processor and operating systems are self-stabilizing, which implies that OS resident monitor recovery, which is part of operating system, is self-stabilizing as well. That implies that eventually each critical process and subsystem will have monitor. Each monitor in itself is self-stabilizing. Therefore, eventually every critical process and subsystem is in safe state. In case that we have corrupted history logs that may cause monitor system corruption, can be basically is solved by corrupted history that causes monitor state corruption does not this case can be solved because if the corrupted history causes recovery, then the recovery action basically trims the history, and we start afresh and accumulate new history log that really shows the system state. In case that history log does not cause recovery action, eventually we will accumulate enough information that reflects the real state of the system and act accordingly. Okay, so the second work I've done, it's called recovery-oriented programming. And it's, yeah.
Some questions about the first part. So first, can you comment a little bit on this state that you actually record? Because if you only say that you record some variables, this sounds like very little. Because you probably have to store file pointers and something about global memory share between many processors.
That depends. Yeah, you have to it's not that we defined exactly what you have to record. Okay. It's your decision that you will have to make because it really depends on the system. Okay, it's something that the person that designs predicates and recovery actions will have to decide what to record. Because the state of a system is quite big, but none of it is important or reflects some kind of information that is important for system health.
Okay. So do we have any formal way to somehow check that we record a sufficient amount of information?
I would say not right now.
Okay.
We weren't able to come up with some formal ideas what you have to record. You have to understand what the system is, what is important, what portion of state is important to see the property to reflect system state health, and just choose to record the important portions. I would say that it's possible to think about some formal formalization of what to record for certain types of systems. Like if it's file system, then you should record this and that. If it's networking system, you should do this and that. But no generic ideas. Yeah.
In general, you seem to presume that there are components which come already a priori with recovery actions?
We assume that there is no. We assume that you have a system and you have some kind of administrator or person or someone that understands it, or maybe even the programmer that wrote it, that understands the system very well, and that provides those predicates and recovery actions.
So, just clarification. So, for the first part you're talking about, are you just like trying to give us some assumption of the? Are you just setting up a framework, or from like? I guess my question is from the practical point of view.
Yeah.
What did we get from this first part, or are you just making some assumption of how your framework is going to work in the next part?
Okay. What I'm presenting is the framework, and then like after the second part, I will introduce a bit of correctness proofs that such systems converge to legal execution from any state. Yeah.
Give us an example of how this is used, an example system that will use this framework to provide recovery?
Well, you can think of, I don't know, anything. Just, I don't know, printing system in big company. Sometimes printing works get lost.
But that begs the question of how hard it is to provide the kind of liveness capturing that your effort seems to require. You know, if you can't in some way understand and capture your liveness actions, you're not going to be able to use your framework.
Yeah.
And so it would be nice to see an example of how that might be done in a system, even a toy system.
Yeah. Well, just because of lack of time, I haven't presented in the paper. We have examples of critical section mutual exclusion algorithm with that is enhanced with predicates and recovery actions, and we show that formally that the whole thing converges to legal execution, stuff like that, or printing system in big organization with some jobs are not being printed because the printers because the format they're bad documents that printers are unable to print and they get stuck on that. So we did such things, but we don't have some kind of real I don't know, mutual exclusion is good enough.
Just to add to that one, I think the biggest challenge in these kind of self-healing system is deciding that we are in a faulty state. I mean, that's the biggest decision, an important decision, and probably most complicated one. And taking into circumstances, the reality of that system, event, polling, a valid event, invalid event, the mixture to make them critical and critical, that's the biggest challenge.
Yeah.
So where does that fit? Let's make it as simple as says, bad, good, in this sort of framework? Or is it that a push to the predicate that says, the administrator know how to correlate the information, put the rules in place that says, if the following happened, therefore,
The second.
Basically, the logic of deciding what is safe state or what's in unsafe state is pushed to predicates and history log.
So is that the premise of the dissertation that says actually a framework?
No, the main idea, the main point was when I started to work on this in this area, the only the things that were done was basically system research, which is very nice. But what it shows is that a certain system works correctly with with certain monitoring recovery layer, but there were absolutely no formal no formalization of those ideas and no proofs, and there was okay, we have monitoring layer and we assume that it works.
Yeah, but there are ways to measure these sort of things, something called availability, when fault tolerance system, when we say 99.9959 and 5. That's the measuring method to represent effectiveness of these sort of recovery mechanism to prove the availability.
But the thing is, usually when you see system paper, it's specific system that has a tailored monitoring recovery layer, and that provides the desired availability metrics, the desired availability. But there's absolutely no generic stuff. Like they claim that they're generic, but no one says that it will work on another system or will provide a good availability percentage in our system.
So that's the angle. Currently, this is generic framework that could be applicable to anything.
Yeah. Yeah.
Oh, so I was to say, so database systems do recovery all the time.
Yeah.
The monitoring that they do is of, I guess, two forms. One, the system crashes, or two, the operator notices that nothing's happened.
Mm-hmm.
I don't know how you would generalize that to, or capture that in what you're dealing with.
Mm-hmm. Well, database crashes, probably you can.
I mean, what would you say? I mean, so nothing's happening for a while. How do you know that the loop that the system seems to be in will terminate at some point with some action, or not?
The system loops if it gets CPU time, like it gets resources, but it does not produce some kind of result over time. Like it's basically stuck in the same state or in loop of the same states without producing result over time.
Yes, but
what is producing result in database? It's getting a response to a request, to database, or responding to some ping.
So the problem here is how do you capture the state appropriately so that you can notice that you have the same state again?
That's the thing. You have to have a very intelligent administrator that is able to understand.
Not an administrator. Nobody. I don't think anybody knows how to do that.
No, I mean, this would an example become query response take normally 5 seconds. Anything that's taking a little bit more than 5 seconds or up to 95%, 7 seconds, will be flagged. If it's passing the 7 seconds, it's an error. Kind of that could be the predicate that the administrator will program into the fault detection engine to say it's time to recover. Is that roughly what?
Liveness, ideally, we would say that liveness should be recorded. Lack of liveness should be identified by state, but one can define it based on time as well. Like if you say that you know that your system should provide response for average query 5-7 seconds.
If you're willing to,
based on time.
If you're willing to accept that, then we have systems that do this.
Sorry?
I think if you're willing to accept that, then we have systems that do this.
Yeah, actually, we have one in this one. We implemented just the release that's coming. We implement exactly like the notion of liveliness, for example. I am isolated. How do I detect I'm isolated? How to go about recovery?
Okay.
So, several sorts of principles.
Yeah.
So, is there any a scenario like you say liveliness? Even the state is still, maybe it goes to when the machine, like let's say, goes into a bad state.
Yeah.
It goes to a random state every next time. It's still liveness, but how do you But that's actually because it just go to a random state every time.
But if this random state is not safe, meaning that it does not respect safety specification, then we'll recognize that. We'll detect that. If this random state is safe, then it's fine. But eventually, you have to think that this random state is not. It goes like when I think about this problem, I think about like that. When we write a perfect, if we would be able to write a perfect software, that would be a software that expects every possible input and provides correct output for that input. Your software is faulty when it receives input, either input that it hadn't expected, or it provides an output that is not as expected for that input. Okay, that's basically you can think about software as a function from input to output. So if this function behaves incorrectly, you should recognize that and invoke some recovery action that will bring it to the initial, to some state from which it executes legally incorrectly. That's the way of thinking about this problem from my point of view.
It's not just the software. You have to deal with hardware errors too. I mean,
Yeah.
so you have to think about it in terms of system errors, not just software errors. Bad things happen in systems, and a good recovery system, a good recovery mechanism will in fact be able to recover from those things and go on.
Because of that, I mentioned the assumption of self-stabilizing processor and operating system, which implies that both processor and operating system running on top of it eventually converge to legal execution, meaning that those hardware faults are being absorbed by the underlying system.
Well,
Yeah, it's very complicated. Some of the people in my group did work on those subjects, so I can give you links to your
When you say work, you consider liveness. So system does something and you wait, we will do something useful. What can you do in full generality? Probably nothing. The only trick is the system is deterministic and you see repeated state.
But it isn't.
It
isn't deterministic.
No, I know it. I say this is one case where you know you will never get out of, you know you are in a loop.
Yeah, the problem that I have with that is how much of the state do you have to capture to detect that?
I'm not arguing with you. I'm saying that in full generality, if even we forget about problems you have, what else can you say? Suppose by miracle we can measure states. In full generality, if system is not deterministic, even if it repeats state, we don't know, maybe it's okay. If it's deterministic and repeats a state, then it's a loop. And probably there is not much to say in full generality anyway.
Yeah. As I mentioned, like if you can maybe define classes of systems, and then maybe you can say something intelligent about state of those systems.
The premise that most people who work in recovery and define recovery mechanisms, the premise is that the failures that bring the system down or cause it to cycle are in fact not deterministic. So that if you repeat the execution, things will turn out better the second time round. That's in fact essential for database recovery, is essential for various forms of application recovery. So it's the reason why logging works. You capture only part of the execution and you try it again. And you hope that the part which was non-deterministic works in your favor the second time round.
So basically, you hope that the environment changed enough so that the second time the execution will work the second time. That's what happens. That's what happens. You hope that the environment changed. Because if the environment is exactly the same as the first time, the application failed, and the application itself is deterministic, then you'll get the same result. So you hope something changed in the environment.
Right.
Okay, so I'll continue. Yeah, no, it was, it's a good thing because it shows that people are interested, that it's relevant to someone. Okay, so the second case is that software package is a transparent box. Again, we make assumption of self-stabilizing platform of processor on operating system, and which implies that processes exist and execute their code. The original system is Eventual Byzantine. Again, we have specification composer that supplies logical expressions on program input and output variables and recovery actions, and programmer that makes best effort on implementation using the same input-output variables as the specification composer, but the system produced by him, written by him, still contains bugs and unexpected states. Pretty much the same setup as previously, except that here we actually can manipulate the code. So the idea is that specifications composer provide subsystems hierarchy graph and recovery tuples. Programmer provides code, and all this inserted into precompiler, and we get the system that is able to recover from any state. So the generated code for one process, so the code with recovery tuples, some code for event-driven monitor is injected into the code. An external monitor thread is created from the recovery tuple's information. We have to have the external monitor as well as event-driven monitor in case that the event-driven monitor section is never reached or it wouldn't be reached after a certain time. We have to have so the monitoring of subsystem goes as follows. The code for process monitoring is inserted, and external monitor for processes are created. And we also have subsystem external monitor thread. So I'll show the examples of the transformation, of the actual transformation and code creation. So in case of safety recovery tuple, we have one process, and the predicate is that x should not be equal to 7, and the recovery action is to restart the process. And in the code, we have the assignment of x to a. So when it changes, so the event of change is basically the point of event-driven monitoring. So we create a temporary variable temp x. It's assigned to a variable that x should be assigned. And then we check the predicate. And if the assignment causes the state become faulty, meaning the predicate is not satisfied, we'll call for recovery actions. Otherwise, for recovery action, which is restarting the thread, otherwise we'll just assign x with a new value. Okay.
When you say restart, do you mean going back to the beginning of time and re-executing?
Yeah.
Just this thread?
Yeah. Well, just this thread, and if the subsystem state becomes inconsistent after the recovery completed, then you'll have to restart all the process in the subsystem and so on.
So the system manages different type of restart rather than one restart that restarts everything. So process restart, procedure restart, data flow restart. These are all, I'm assuming, different options.
Yeah, you may have a list of options. One would be just wait, and the environment may change. Release some resources or add some resources, and the last option is always restart.
So it's a repair function.
Yeah, repair. Try to change the environment. So maybe next time. So maybe after that change, the system will be in better position, and maybe it will work.
Is this precompiler a real program that you have?
Yeah, we made a prototype.
So what can be X?
Any variable. What?
How do you manage aliasing?
Okay, we did a prototype. We didn't do the full scale precompiler that works in any case.
It's impossible to write one. It's impossible to write one. Yeah. Okay.
I think
but why not? You basically you can say that you're looking at the addresses of variables, not the variable names.
Okay,
so it can be done this way. Mm-hmm. You just have to work a bit hard. The precompiler we created is very basic, and it's simple, but just to see that things work or the ideas are sound. You'll just have to work a bit harder to make it real. Okay. So as I mentioned before, this slide should be there. We have to have external monitor in case that we don't reach the section of event-driven monitoring. Okay, monitoring of liveness property. The invariant is, for example, the invariant will be eventually x plus y equals 15. The recovery action is restarting the thread, and the history trimming rule, meaning that if liveness event happens, is just clean completely. In some cases, when in the paper, there are much more complicated examples. So sometimes you remove certain entries in the history log that are relevant for certain process or certain subsystem. So the code is here increasing x by 2 and increasing y by 5. So the procompiler transforms it to the checking that if when x is assigned new value, checking that x plus y equals 15. If it does, then the history trimming rule is applied, and the history becomes empty. Again, same with y. When y is changed, we check the liveness rule, and if it's if it has been if liveness rule is satisfied, the history log is trimmed. Sorry, I just wanted, okay. I can't, like, there's some problem with animation. Anyways, what I meant to show here is that there is an external monitor that looks at the history log. Every time it's scheduled, it checks the history log for identical entries, and if there are identical entries, then the recovery action is invoked.
Log of states become very, very, very long.
Yeah.
And so actually testing your invariant could in fact become very, very, very expensive.
Yes. But in real life, I think when you write such systems, you will find ways to optimize it, meaning that compressed state. What I mean is that if you have integer variable, it does not, like in any normal program, I think, integer variable never gets the full range of integer. It will get like values from 1 to 3,000, something like that. So you can you can actually design precompiler to check those, to minimize the range of variables, to find the real range of variables, and then you know that your state is much like you don't have to keep the integer. It's enough to keep enough bits to maintain values from 1 to 3,000. You can compress the state to keep it smaller. Well, nothing is ideal, never. Otherwise, there wouldn't be research and there wouldn't be unsolved problems. Okay. So monitoring of subsystems, the subsystem recovery, subsystem predicates are checked only by external monitor, and the history log, the history log entries are recorded using distributed snapshot algorithms. Okay, so I'm getting to the point of the hill. I've presented basically the two generic frameworks for black box software and transparent box software. So what I wanted to show is that is to provide correctness proofs that those architectures create basically software that is able to converge to legal execution from any given state. So we defined an execution E to be a restart supporting fair execution if and only if E is a fair execution in which every subsystem that is initialized during E respects a specification function, which basically means that after restart, subsystem is known to execute correctly. So what we want to show is that every RSF execution E has a suffix in which the system respects its specification function. Very generic and very high-level correctness proof. Assumption. We know that processes and external monitors are scheduled fairly due to presence of self-stabilizing software platform, the processor and operating system. Safety is achieved because process either reaches monitoring section in its code or its external monitor makes a scheduled check and discovers lack of safety. In case of subsystem, external monitor makes a scheduled checks and discovers lack of safety. Liveness. The process or subsystem external monitor makes a scheduled check of the history log and discovers lack of liveness, as we discussed before, meaning that there have been two identical entries describing this two identical entries of subsystem state, while subsystem processes have received CPU time and resources. In case in case the history is corrupted, it's not a problem because it either causes a recovery action and then the history log is streamed, or new correct records are eventually accumulated and they reflect the real state of the system and recovery action is taken or not. So the second part of my dissertation is a bit on another direction, but it also has to do with creating or producing correct software for a given environment. In this case, I present the work called Automatic Control Search Engine for Dynamic Environment. And here we make absolutely no assumptions on possible environment changes. We assume that one can experiment on replicas of the environment, that we can make experiments parallel, which allows us to have polynomial search time due to parallelization and due to exposing of systems of environment state, meaning that we're able to actually observe the environment state and set environment to a certain state if required. So I go into defining system settings. The environment. The environment is large, sophisticated, dynamic. It's non-deterministic. Basically, it's non-deterministic infinite automaton. But we claim that at every given time slot, the environment is either deterministic finite automaton or probabilistic finite automaton with a given transition function. So the control, the program, interacts with some part of the environment, which we call plant. Okay, so instead of interacting with this huge non-deterministic environment, we know that control interacts with plant, and plant interacts with the environment. So if you think about the example, is that imagine you have a car that rides on a road, like on Earth, on planet Earth. So basically, the control is you sitting behind the wheel and, steering the wheel, pushing the gas pedal, and so on. The car is the plant, and the environment is the plane the car rides on. Okay. So basically, the idea is to find the control, the sequence of steering the wheel and pushing the gas and brakes pedals to achieve a certain movement of the car on a plane. Okay. We assume that the environment is reentrant, meaning that we can execute two experiments at the same time and they do not interfere with each other, and that it's history oblivious, meaning that we can execute the same experiment twice and get the same results. Okay, so we want to find the control. We have the control generator that receives as a that receives as an input list of goals, behaviors, how the plant should behave. Okay, how the plant should behave in the environment. Okay. And there is some kind of observer that records the plant-environment interaction and provides feedback to the control generator. And if we find a control, meaning list of inputs to the plan that cause the plan to interact with the environment in a certain way, basically found what we wanted. So, yeah.
You want to eventually find this control, or?
No, So we basically have an experiment. We have one big environment, a list of, a collection of replicated environments with plants, like environment and plant. Okay, we have them together. We have those. Doesn't matter, like as many as you wish. You produce all possible controls that may provide a desired behavior and try them. And then you find one control that, like, if you find one or several controls that work, and output that control. You have no knowledge because the environment is so big, and it's non-deterministic and it's infinite. You cannot learn it. You have no knowledge about it, or maybe you had some knowledge, but but now it behaves in such a way that you don't know nothing about it. So you're basically searching for control in runtime.
Okay, so then I don't understand the role of the observer. Why the control generator needs anything about the interaction between the particular particular environment, a particular
plant, because that's the interaction between plant and environment is the we're looking for control, for certain control. Control is basically a list of inputs to the plan that cause it to interact with the environment in a certain way. Like if you think about the example of car riding on a plane on a surface, you want a car to ride in a certain way, in certain speed, and not deviating from the road, and so on and so on. We have to finish. Okay, so basically that's the idea. We present list of algorithms for various environment settings, meaning what you can do if you have ability to expose environment state or set it in a certain state, you can produce quite efficient algorithms in the sense that they are parallel, so the one search is quite short, and so on and so forth. It's quite a complicated paper, and well, I'll go to the last slide just to put the conclusions on. So basically, I've presented two sections of my research. One was about presenting generic monitor and recovery layer for existing software for cases of black box and transparent box. And the second one is self-star programming, a framework for finding control for an environment dynamically. Okay, this is it. If you have questions, remarks. Yeah, please. Thanks.
So on the first, you were saying there's an underlying self-stabilizing platform.
Yeah.
I was kind of hoping for what.
Well, other people in my group worked on those ideas. About the processor, there is, as far as I know, there was like a design. There was a design. Obviously, we haven't built a real processor. But there was very very detailed design how to make it. As far as I remember, it has to do with putting a self-stabilizing watchdog that made the processor to return to correct state if it deviated. And there also was a prototype of self-stabilizing operating system. It was very basic because non-basic version it's huge amount of work. There was the basic version of self-stabilizing I/O, self-stabilizing device driver, self-stabilizing file system, I think, and so on. So, yeah, if the thing is, with every when we in general talk about some kind, like almost all work in this area has the same architecture of a system that is not perfect and some kind of monitor recovery layer. What we claim is that that layer itself is a software. It can be faulty, and it also can be affected by underlying software platform, meaning operating system and so on. So even if you make it completely correct, you verify it and so on, you have to have the underlying system, operating system working correctly all the time. So you have to have a stack of self-stabilizing components to have a truly self-stabilizing system. You cannot avoid it. But maybe what you can do is to have some partial guarantees of legal execution, and that you know that for a certain amount of time your system executes correctly, and then if it reaches illegal state or something like that, you can realize that and cause invoke recovery actions and so on and so forth. But there is no way around. There is no way to avoid mistakes in underlying layer. Like if you build those monitoring recovery layers that are very good, but if you have underlying faults coming from processor operating systems, you have to deal with that as well. There is no way to avoid it.
But the self-stabilizing assumption does not imply that there are no faults coming.
No, the opposite is true. The opposite is correct. That any self-stabilizing program is designed to be self-stabilizing because they know that there are faults and you need to overcome. You need to
fault tolerant systems. You have duplication one down the other thing. That's stabilization.
So
no,
is,
basically that duplication. That's fault tolerant technique. But self-stabilizing program is something else. It's basically a program that exploits the all states, and
let me clarify.
Yeah.
If I have a single processor and have a hard failure, the system cannot stabilize itself.
Yeah.
In order to stabilize it, you have a redundant system where
you have several processes and you sweep it to other processes.
So redundancy becomes.
well, I would argue that a dead processor is a stable system.
That's just like the car that is very stable but doesn't move. Yes.
Right.
But it's not live, unfortunately.
But yeah, you have to ask
So,
yourself.
It's stable enough, but the thing is, it's stable enough for a user that works on PC for for several days without shutting down the computer or some system.
Sure.
But if you send something as were cases of robots sent to Mars and they work without stopping for several years, they actually accumulate some faults. That's a problem. And the funny thing, I think, as the technology progresses, we actually have more and more systems that don't shut down for very long periods of time, such as banking systems, cloud computing, storage system. So, and the thing is, you cannot debug them for infinite long time. Like you can debug them, for example, for a year, but after that you want to put it out and ship it. But you cannot. You either do full verification or you do some kind of monitoring and recovery.
Yes.
Okay.
It's not exactly what you work with. It's sort of related to stabilization. There are biological systems that stabilize. Did people look and try to learn?
I think it's another area. It's called neural algorithms, genetic algorithms. There is a huge field it's called genetic algorithms that do exactly that, biological inspiring computing. But you can say that I'm not really familiar with the work in this field. As far as I understand, you basically have some kind of fault tolerance mechanism built into the system that are I don't have much to say because it's completely. But there is a huge field that works on that. As far as I understand, they usually concentrate on a certain problem, and they solve it with biology-inspired techniques. But they're not. As far as I know, there are no generic tools that say, okay, we saw some kind of recovery mechanism in this and that biological creature, and we'll produce a generic framework. There are no such things, but they usually work on a certain algorithm and solve the problems with biology-inspired tools.
Yeah, and this area is actually not connected anyhow with recovery. This is just a direct random search for algorithms. That's what genetic algorithms are.
Yeah, I know genetic algorithms, but biological systems do recover.
Yeah,
Often. Not always. On the other hand, you don't want to do everything like nature, say airplanes don't flap their wings.
Out of the box thinking, we just have a flat wings.
So, thank you for provoking discussion.
Okay, thank you.
Thank you.